Hello, and welcome to this recorded learning module for designers targeting Xilinx's programmable FPGAs. My name is Frank Nelson. I'll be your instructor for this module. This module is about the Xilinx Agile mixed signal solution. Now, this module introduces the Xilinx Agile mixed signal solution enabled by the Xilinx 7 series device architectures. This module will also show you some key benefits and features that are enabled when using the Xilinx Agile mixed signal solution. In this module, we'll be looking into the different architectural aspects of the analog functions that enable the mixed signal design within a Xilinx FPGA. We'll also look at some example applications and show how we can apply this technology in certain targeted applications. This module is part of our Designing with the Xilinx AMS course. Now, we recommend that you take the time to attend this course to learn all the critical design considerations you must make when targeting any FPGA device using the AMS solution. Xilinx FPGAs have been delivering solutions for high performance and high volume systems for years. The strength of an FPGA lies in configuration, signal processing, and control capability, as well as digital connectivity. Now, we live in an analog world. Everything that we see, feel, or hear is analog in nature. Many diverse electronic systems designed today are aware of their physical environment and are capable of processing such analog information. The systems might have to interface directly to the real world through sensors to monitor and control the environment. Data converters, such as analog to digital converters, or ADC, and digital to analog converters, DACs, provide this critical bridge between the digital and the analog worlds. Xilinx's FPGAs are now increasingly common in applications which interface with the physical world. For example, industrial automation applications. Other examples include applications which monitor the operating environment to ensure safe and reliable operation. For example, monitoring temperatures and power supply conditions in a communications infrastructure applications. Now here, the FPGA can deliver the flexible control and signal conditioning necessary to match system requirements or deliver flexible protocol for a variety of I/O standards and memory interfaces. Xilinx has provided the system monitor capabilities on our high-end FPGAs for several generations with an eye toward monitoring power and voltage. Our customers demand more, so we improve the system monitor by doubling the number of ADCs and improving each ADC's sample rate by a factor of 10. This updated analog interface is referred to as the Xilinx Analog to Digital Converter Module, or XADC core for short. A wide range of sensor types are required to measure the physical environment. These sensors produce an electrical output in response to stimuli from the environment. For example, temperature, moisture, as well as mechanical stress. Now, the output signals from these sensors vary greatly and must be manipulated or conditioned to map the sensor output signal to the input range of the analog to digital converter before it can be processed in the system. Now, there is often the need to calibrate, i.e. remove the offset and the gain errors, the analog signal processing chain, and perhaps remove nonlinearity associated with the sensor itself. While many of these functions are commonly implemented in the analog signal processing chain or sometimes in a microcontroller, they can be more efficiently implemented with the digital signal processing capabilities of an FPGA. Now, this is especially true for high channel counts and where complex filtering is required in a system. Calibration using the FPGA can significantly reduce cost by eliminating components and reducing the PCB footprint of analog circuits. It can also provide a platform that is easily reprogrammed to address a range of sensors and application needs. However, the analog to digital converter, the ADC, is the key to enabling such an approach, and the Xilinx ADC core in the 7 series FPGAs provides unique flexibility and functionality beyond which are typically found in ADCs integrated into microcontroller units. The 7 series Agile Mixed Signal, or AMS, approach now delivers the industry's most flexible general-purpose analog interface. The programmable XADC core and the logic in the FPGA enables customization for a wide variety of applications, from simple control and sequencing to more signal processing intensive tasks like linearization, calibration, and filtering. The signal processing capabilities of the FPGA can also be leveraged to enhance the performance of the analog to digital converters using new techniques of oversampling and averaging. Now, this flexibility replaces the need for the diverse catalog of analog devices required today. AMS is a combination of programmable XADC cores and programmable logic that is unique to the 7 series FPGA device families. Whether complex analog signal conditioning or simple analog monitoring, the Xilinx Agile mixed signal capability is worth looking into for your next application. Before we delve into the architectural specifics of the XADC, which forms the core of the AMS solution, let's look at some of the benefits that AMS provides by integrating an analog to digital converter inside of an FPGA. The first and probably the most obvious benefit is that you're reducing the overall cost of your solution. Now let's look at the following figure, which illustrates a simple controller board that includes a 4-channel analog to digital converter, a small microcontroller, as well as an FPGA. Now, whether it is a motor control or an energy management system, typically there is a DSP or microcontroller unit which performs the housekeeping functions. The discrete ADC performs an analog to digital conversion of the input signal for the MCU to process. Sometimes the analog to digital converter is integrated into the DSP or the MCU device. Now, very often there is an FPGA in the system which performs the network interface or some protocol conversion function. The configurable nature of the FPGA allows you to customize the solution depending on what kind of networking interface or protocol conversion is needed for your system. A single chip solution can be realized when you use a Xilinx FPGA with the programmable XADC integrated and implementing a soft microprocessor. This brings down the cost and complexity of the overall system, especially if you're talking about an RTX device or FPGAs around the $10 price frame for the applications that we're targeting. In this case, it would add an awful lot of value. Now, the single device solution not only simplifies the bill of materials and reduces cost, but also provides improvements in board area, pin savings, fit improvement, and better inventory management. The second advantage is customization. Now, digital designers experienced with FPGAs can use the programmable logic to customize the XADC core to address the diverse needs for analog signal processing, such as application-specific calibration, linearization, as well as signal processing needs. Now, the 7 series FPGAs, as well as the Zinc Extensible Programming Platforms, or EPPs, can be programmed to address a wide range of functionality, including complex control and management through a microprocessor, digital signal processing, and general monitoring and control capabilities. The flexibility that the programmable logic offers enables designers to tailor an analog solution that meets the exact needs of their system. The third advantage is enhanced reliability, safety, and security. Agile mixed signal contributes to higher reliability because using fewer devices translates into an improved fit rate. The interface to the on-chip sensors provides factory-guaranteed measurement accuracy that can be used for built-in self-test functionality to ensure that equipment maintains operation within its thermal limits. The power supply and device temperature information of the chip, including the off-chip signal monitors, can be accessed via the JTAG interface or through the FPGA fabric. These signals can be monitored with the ChipScope tool, even without instantiation of the XADC core into your design. The XADC device operates in a predefined mode called the default mode that monitors on-chip temperature and supply voltages. Another security feature that the AMS provides is protection of the FPGA design from a hack or physical tamper of the system enclosures. This feature may be useful for aerospace and defense or even commercial customers where the FPGA is carrying encrypted or secure information and want to protect their IP from any developed side channel attack. A side channel attack is an attempt to hack the FPGA designs by physically manipulating the system through temperature and power supply. Now, designers can prevent such side channel attacks and physical tamper of systems by using the XADC module. The XADC module can be used to detect the operating conditions outside and put the system in a mode that it becomes less vulnerable to hack. The XADC core is the basic building block that enables Agile mixed signal functionality in the 7 series FPGAs and the Zinc EPP. The XADC core can access up to 17 external analog input channels. There is a single dedicated analog input pin pair, the VP-VN pair, available on the Xilinx package, and the remaining 16 auxiliary inputs use the dual-purpose I.O.s on the FPGA. Now, these FPGA digital I.O.s are individually nominated as analog inputs when the XADC core is instantiated into a design. The analog input channels are very flexible and support multiple analog input signal types. Now, you can program the input to cope with bipolar or unipolar signals. The analog inputs of the ADC core use the differential sampling scheme to reduce the effects of common mode noise signals. This common mode rejection improves the ADC's performance in noisy digital environments. The differential inputs in the bipolar-unipolar modes provide support for a wide number of sensors. Remember that some analog signals limiting may be necessary to protect the analog inputs on the FPGA. Now, the XADC also includes 6 on-chip sensors that support measurement of the on-chip power supply voltage through 5 channels and a die temperature through 1 channel. The on-chip sensors and the external analog inputs are multiplexed and are available to the 2 ADCs. These ADCs may be configured to sample in continuous or event-driven modes. The XADC core includes a separate track and hold associated with each A to D converter, which enables much higher throughput rate. The function of the track and hold circuit is to sample the analog front end and hold its voltage constant during the interval required for the ADC to perform the analog to digital conversion. The track and hold circuit performs sampling at much higher rate than the ADC, thereby improving the overall throughput. The track and hold also contains signal conditioning capability. And at the core of the XADC are the 2 12-bit 1 megasample per second ADCs. Now, you can run the ADCs independently and simultaneously in order to sample 2 channels at a time. That is particularly useful in a motor control application or any application where you want to preserve the relationship, or the phase relationship between 2 channels. Now, the ADC conversion data is stored in dedicated registers called the status registers. These registers are accessible via the FPGA interconnect using a 16-bit synchronous read and write port called the Dynamic Reconfiguration Port, or DRP. The DRP interface can run at extreme rates as high as 250 MHz, allowing designers to perform customization between the conversions if necessary. The ADC conversion data is also accessible via the JTAG. In this case, users are not required to instantiate the XADC core. The dedicated interface uses the existing FPGA JTAG infrastructure, which can be directly accessed using the ChipScope tool. As discussed earlier, if the XADC is not instantiated into a design, the device operates in a predefined mode called the default mode. That monitors on-chip temperature and supply voltages. The XAD operation is user-defined by writing to the control registers using either the DRP ports or the JTAG interface. It is also possible to initialize these register contents when the XADC is instantiated into a design using the block attributes. The XADC core can generate alarm signals on the logic outputs when an internal sensor measurement exceeds some user-defined threshold. The alarms are simultaneously written to the appropriate status registers. If averaging has been enabled for a sensor channel, the averaged value is compared to the alarm threshold register contents. To allow access to the status and control registers from the FPGA logic, the XADC block must be instantiated into your design. The figure in this slide shows the ports on the XADC primitive. The XADC core can be customized using the core generator tool and then be instantiated into your HDL design. The XADC core generator wizard basically pre-configures the status and control registers while the core is being generated. It is also possible to initialize these register contents when the XADC is instantiated into a design using the block attributes placed in your HDL code. The XADC operation can be user-defined at runtime by writing to the control registers via the Dynamic Reconfiguration Port. With the processor IP cores available for FPGAs, it is possible to create an autonomous processing platform which can configure and control the XADC core. After the analog signals have been accurately converted by the analog to digital converters, the logic resources in the FPGA, which include the DSP slices, block RAM, and logic functions, can be applied to correct or calibrate the transfer function of the sensor. By oversampling and using the signal processing capabilities of the FPGA, the resolution of the analog channel can be greatly enhanced. With the configurability advantage of FPGAs, it is possible to create an autonomous processing platform. An autonomous processing platform enables an intelligent analog subsystem that encapsulates functionality and helps to control and manage analog chores, thereby freeing processing cycles and ensuring quicker response times. It also enables the integration of DSP as needed and eases design, test, and maintenance activities. And because it eliminates the need to use a higher performance processor, it also contributes to lower system cost. Implementation of the analog interface or data acquisition is just one aspect of designing the entire system. The data acquisition system must also be integrated into what is often a complex digital or embedded control system. FPGAs are commonly used to implement sophisticated signal processing algorithms or act as co-processors to the microprocessor in such systems. Verifying the data acquisition together with the digital control system can be a complex task. Now, the Xilinx toolchain supports verification of the design by providing a simulation model of the XADC functionality, which can be incorporated into the digital verification flow. Digital designers can add some analog signals to the simulation when doing verification. The simulation model will allow signals for a number of sources to be introduced into the simulation itself, such as real measurement data for the bench or simulation output data from a tool like MATLAB or Simulink. The Agile mixed signal subsystem is optimal for replacing a wide range of discrete analog circuits responsible for system-level or housekeeping functions. It is targeted to address the diverse needs of different markets and applications. The table in this slide provides a list of markets and applications that can be addressed using an Agile mixed signal solution. We will be looking into a few applications in further slides which will illustrate the benefits of the Xilinx AMS solution. As an example of the benefits of an autonomous processing subsystem, the following figure shows an integrated high-performance motor controller. The high-performance motor controller is based on the XADC block, which is includes a soft core MicroBlaze microprocessor, DSP blocks, as well as support logic functions, including pulse width modulation, counter timers, and serial communication channels. Now, in this application, the two analog to digital converters in the XADC block are configured to do simultaneously sampling of the two-phase currents. The speed of the motor can be synchronized to the measured sampled phase currents by varying the PWM signal via the GPIO resources. Using a simple application programming interface, or API, a central control processor can issue high-level commands to configure and control the autonomous subsystem. The subsystem controls motor functions independently of the central microprocessor and reports back status or issue interrupts as appropriate. Separating the motor controller operation through an autonomous solution encapsulates the solution, making the overall system easier to design, test, and maintain. This can also lead to lower costs and overall higher system-level performance. If you want to know more about the EDK flow and how the design is simulated, consider watching the AMS EDK flow REL on this same site. The popularity of touch sensing interfaces has been rapidly increasing, especially with the emergence of smartphones and tablet computing. While there are multiple technologies used to manage touch sensing, one of the most popular methods is resistive touch. The following figure shows a simplified 8-wire resistive touchscreen that has been implemented using an Arctic-7 FPGA. In this example, the touch sensor and microprocessor are integrated, reducing device count and lowering the overall system cost. The Arctic-7 FPGAs and the Zinc 7000 EPPs are well suited for implementing both resistive and capacitive sensor interfaces. Using the XADC block, the Xilinx devices can directly measure sensor voltage. The FPGA then processes the samples, compares the values to the thresholds, and manages the touch or touches. As shown in the figure, only a small amount of FPGA fabric resources are required to do this. Moreover, even the smallest, lowest cost Arctic-7 device has plenty of resources remaining for many additional functions. Beyond the benefits of system-level integration, the high-performance FPGA's logic resources allows for fine-tuning of touchscreen processing algorithms, which can quickly exceed the processing capabilities of the most standalone touchscreen devices. Now, this expanded processing capability in turn can allow for a superior human-machine interface that is optimized to the application needs or the characteristics of the touchscreen materials. Another touchscreen application is a point-of-sale terminal. In this case, you can use the second ADC to monitor for an anti-tamper situation. The XADC can be instantiated into the design where one of the ADCs is assigned to do the touchscreen operation. In this situation, the second ADC is assigned to monitor the sensors to detect any physical tampering of the EPOS enclosure. Another application of the XADC core is when it is used as a general-purpose analog interface to measure currents and voltages of external sensors. Many sensor applications have a number of functions in common, so there's often the need to calibrate, i.e. remove offset and gain errors, for the analog signal processing chain and perhaps remove nonlinearity associated with the sensor itself. After the analog signals have been accurately converted by the ADCs, the logic resources in the FPGA can be used to correct or calibrate the transfer function of the sensor. However, the ADCs carry out a full 16-bit conversion. It still complies with a 12-bit specification, which significantly reduces the quantization error or noise. The additional 4 bits of precision can be used to improve resolution through averaging or filtering. To linearize a sensor transfer function, one approach might be to use an interpolated lookup table in the form of a single 1K by 18 block RAM. Linearization of a large number of channels is very efficient to implement in an FPGA because the same resources can be shared across all channels due to the high clock rates that can be achieved inside an FPGA. The oversampling capability of the ADC, up to 1 megasamples per second, and the ability to implement digital filters with a range of response types, along with any stop and pass band requirements, can greatly reduce the analog filter requirements. Simple passive low-pass filters can be sufficient to suppress higher frequencies and prevent aliasing effects. Xilinx's system generator for DSP applications is the industry's leading high-level tool for designing high-performance DSP systems inside an FPGA. Even for non-digital designers or analog engineers with limited FPGA experience, implementing DSP functionality inside an FPGA has become a lot easier with a system generator tool. Now, Xilinx's system generator is based on Simulink and MATLAB software and has a block set of functions required for signal processing, such as for filters, arithmetic, as well as other digital logic resources. Now, analog designers with a deep understanding of the sensor type and channel requirements can easily develop compensation algorithms and directly target FPGA implementation using the system generator tool. The XADC subsystem is available in all families and all devices in the 7 series FPGAs. This also includes the RTX device subfamily, which enables implementation of low-cost integrated sensor applications. There is an incredible amount of resources and I/O resources supporting various standards that can be leveraged to perform the signal conditioning, processing, and digital networking required for systems with these devices. The XADC is also integrated into the Zinc EPP, which leverages the Xilinx 7 series programmable logic device family. The EDK system environment provides an XADC-AXI IP using an AXI interface, which is an internal industry standard data bus. The XADC-AXI IP can be used to directly communicate with a processor subsystem, whether it is a dual-ARM A9 core in a Zinc 7000 device or a MicroBlaze soft core implemented on a 7 series FPGA. The autonomous operation of the analog subsystem functionality offloads the main processor and encapsulates the analog monitoring and control, providing known and predictable operation. You can begin to evaluate the XADC subsystem today when you use the Kintex 7 with the ISE version of 13.3 Design Suite software. The AMS targeted design platform includes a targeted reference design so you can see how this feature works and how to get your design started right now. Now look out for the AMS demonstration recording, which will give you an overview of the AMS targeted design platform and the targeted reference design, which can be used to evaluate the XADC block on the KC705 demo board. In summary, Xilinx's Agile mixed signal technology offers a better way to scale and customize common analog interface requirements. This technology is a unique combination of a flexible analog interface, that's the XADC block, and the programmable logic capability of the 7 series FPGAs and the Zinc 7000 extensible processing platform. Now, the key benefit is the ability to customize the data acquisition solution in the digital domain. This allows designers to define a platform that addresses a wide range of requirements to reduce development time and component cost. Other benefits include better support for verification of the analog interface in an HDL simulation, as well as the ability to integrate a wide range of proprietary analog ASSPs into your FPGA application. Well, there are lots of places to learn more about Xilinx FPGAs, and they all start at support.xilinx.com. To learn more about Xilinx AMS solutions, you can visit the microsite you see on this slide. This is where you can find the latest and most updated information about Xilinx AMS solutions. You'll also find some additional white papers about Agile mixed signal solutions at this link. You also have the opportunity to learn more about AMS applications when you attend the Avnet AMS workshop at the 2012 XFest. That's a Xilinx festival. Now, if you would like to register, you can check out the URL you see on this slide to learn more about it. However, if you have questions, and those questions have to do with the 7 Series silicon features, you should refer to the device user guide or check out one of our 7 Series recorded e-learning modules. They're at the same location on our page that you found this recording. Now, if you would like to see what other courses we offer or what other free RALs are available, you can go to the Xilinx education link you see here on this slide as well. I would also like to mention again that there are several instructor-led training courses that we offer worldwide. They cover topics ranging from HDL code to detailed architecture training on the 7 Series device family members. But whatever you do, please take a second and let us know what you thought of this recorded e-learning. Just click on the icon on the next page and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the AMS Overview Recorded e-learning. Thanks for your time and attention, and thanks for your business.